All right, in the last lecture I talked about what happens when sodium chloride dissolves in water. And a couple of really important things. One is that, as we know, the sodium and the chloride separate, and the water molecules, which have lone pairs of electrons on the oxygens, the water molecules point their oxygens at sodium, like so. And they point these lone pairs, two on each oxygen. And those electrons, of course, mean that you have a slight negative charge on the oxygens and a slight positive charge on the hydrogens, because, of course, the molecule as a whole is neutral. And so sodium ions in solution are surrounded by these water molecules like so, and the chlorides sit in between the waters and are separated from the sodium ions by all these water molecules. So, as I said, the properties of sodium chloride in solution are dramatically different from the properties of solid sodium chloride, because in solid sodium chloride the sodiums and the chlorines surround one another directly, directly electrostatically bonded. But in solution they are separated. And what we can do then is we can plot, as I said, make a plot of the chemical potential of sodium chloride as a function of concentration. Sorry, let's make that positive. And low concentrations are down here. And we find that there's a linear region, like so. And then the relationship becomes rather non-linear until at some point we reach saturation. And here is the free energy of pure NaCl. And what we do in solution chemistry is we take advantage of that linear region and extrapolate it to concentration 1, RTLN NaCl concentration equals 0. And we make that intercept there, which I've drawn a little uncomfortably close to the free energy of pure NaCl, we make that our standard state value. And we can derive that for Na plus and for Na and for Cl minus. We can separate them, we can separate the properties of the two ions by various electrochemical methods. So that is our infinite dilution standard state, and the activity of Na plus with that standard state is equal to the concentration of Na plus, where that is in moles per kilogram of water, or molar. Okay, so that's a sort of a brief summary of what we did. What I'd like to think about now is what happens with other ions. We've taken sodium, we've looked at sodium and chloride, they behave like this. And other ions that we're particularly interested in earth sciences would of course be things like silicon, aluminium, so on. Okay, so if we considered silicon, as we know, formally the charge is 4 plus. And silicon is a very small, highly charged ion. And of course, when we dump silicon into water, this effect here, the attraction of the water molecules, is going to be incredibly strong. In fact, the attraction between the highly charged small silicon ion and the water molecules is so strong that the silicon literally tears the oxygen out of the water. And so what happens is that the silicon becomes bonded, directly bonded, to 4 oxygens. Of course, we know that's what silicon likes to do. It likes to be tetrahedral. So when we add water to silicon, we end up with a molecule that's tetrahedral, 4 oxygens. So in solution, silicon is not Si4 plus. Si4 plus cannot exist. It is 4 plus at the center of 4 OHs, each of which has a minus sign, if you like, to give them formal charges. So the net molecule is neutral. It has 4 OHs and a silicon 4 plus. So the net molecule is H4 SiO4 zero charge. So that is that's what happens to silicon in solution. It's dramatically different from sodium and chloride, and the reason is because it's small and highly charged. So we could think about some other small, highly charged ions which are important. One is carbon, again 4 plus. And the same effect would happen with carbon. If we dump pure carbon into water, then it will go through this process which is called hydrolysis, in which the ion is hydrolyzed, it adds water to it, if you like. And for carbon, we have various possibilities. The carbon likes to form 3 bonds in a plane, like so. And get this right, if it's neutral, that isn't right. Okay, I had to stop and find the board cleaner. So I was saying that carbon 4 plus shows similar behavior to silicon. Its bonding, it prefers to be surrounded by 3 oxygens. Each of these would be formally 2 minus. So that lot together would be CO3 2 minus. Okay, but of course this charge likes to attract hydrogens, so we can neutralize one of the charges like that. So that would be a net 1 minus, that would be net 2 minus, and that would be net 2 minus. So that is HCO3 minus. And if we add another hydrogen, we get H2 CO3, and the net charge on that is 0. Oh, this time it does appear to be recording. Good. Okay, so carbon can form carbonate, bicarbonate, or carbonic acid. And the stabilities of the different species, which all can exist in solution, the stabilities of the different species will depend on the hydrogen ion concentration, very obviously, or the pH if you prefer, which obviously most people do prefer. Okay, what other ions behave like this? Well, aluminium is another one that's rather important. In solution, aluminium again is very small, it's moderately highly charged. So Al3+ exists in solution, again at certain pHs. And then we can add hydroxyls. And each time we add one, we reduce the charge. And AlOH30 is the most hydroxylated of these aluminium species that we need to worry about. Okay, so coming back to ions which tend to be single in solution, single ions, like sodium and chloride that I already talked about. That is not complex with oxygen. These are the ions which are large and have low charge. So we look on the far left of the periodic table and the far right of the periodic table, and we find sodium, of course, we've already talked about, potassium, cesium, and rubidium. And in group 2, magnesium, calcium, strontium, and barium. And then on the other side, we look to the far right of the periodic table. So the halogens fall into this category. So F-, Cl-, Br-, and I-. And then in group 6, we have oxygen, O2-, that doesn't really exist in solution. It's either OH- or H2O. It's rather too small to form a single ion. But sulfur can exist as S2-, but more commonly as HS- or H2S. Uncharged. Okay, that is the reduced form of sulfur. As we know, sulfur also has an oxidized form, sulfur 6+. And in this case, as you might expect, sulfur of charge 6 is small, highly charged, and it behaves much more like carbon and silicon. So we can make, normally in solution, SO4 2-. Okay, so our 6+ is surrounded by 4 oxygens, each of which have a -2. So 6 - 8 is 2-. So that will be the more normal form of SO4. We can also have HSO4-, and under extremely acid conditions, H2SO4 0. Okay, so that's the sort of basic introduction. All of these we're going to treat with our infinite dilution standard state. And what I'm going to do now is I'm going to think about a nice simple weathering reaction. Let's suppose that you have a potassium feldspar, say, and that's being weathered. And we need to write down a weathering reaction. So we'll write down potassium feldspar. Let's suppose it's in a granite, which we think is a very nice building material, but actually if it's subjected to acid rain, this potassium feldspar breaks down. And it breaks down to a white platy mineral called kaolinite, Al2Si2O5 OH4. I always have to check that I have the formula correct because I don't look at it from one year to the next. So kaolinite, this is a common weathering product of feldspar. It's white and platy, and of course it's very important economically. It goes into all sorts of products. Paper, rubber products. And the various grades of kaolinite, some are used as filler in the paper, and some is used to give the nice shiny coating of paper like you see in the Sunday supplements. Kaolinite is very important economically, and of course there are important economic deposits of kaolinite in Cornwall, where the granites, particularly the St Austell granite, has been weathered. So we need to balance this reaction, of course. So our feldspar, we're balancing the aluminiums. I'll tell you why in a moment. Obviously, it releases potassium, and as I've written the reaction, it's going to release. Have I written it here? Yeah. Yeah, okay. So I balance the silicas, and my reaction, of course, if I want to consider this in terms of thermodynamics, has to be charge balanced as well. And so what's happening effectively is we're adding hydrogen ions to our feldspar. And obviously we have two potassiums here. We've got two hydrogens there. And I'm going to need, because this is happening in aqueous solution, well, we find out, let's have a look. We've got our charges are balanced, our aluminiums are balanced. We've got 6 silicons, and there's 2 and 4 is 6. And we've got 4 hydrogens here, and 2 hydrogens there. So what we can do, because it's an aqueous solution, we can add water. That's our 2 hydrogens, and that should now balance, he says. So 4 hydrogens, let's check the oxygens. 16 oxygens, 17 oxygens, 5 and 4 is 9, and 8 is 17, hurrah. Okay, so this reaction, feldspar is reacting with acid, the hydrogen ion in water, and water, to produce this platy mineral kaolinite, releasing potassium to solution and in the way I've written it, precipitating quartz. So for this reaction, the standard state free energy change at 298 degrees K we take the standard states of feldspar and kaolinite to be the pure minerals. At the pressure and temperature of interest. We take the standard state of water to be pure water. Okay. And for our ions, for K plus, obviously quartz goes in there, K plus and H plus, it's our infinite dilution standard state. That is a 1 molar solution at infinite dilution in water. Infinite dilute in H2O. Right. So given those standard states, we have a standard state free energy change. Delta G0 is minus $40,910 joules, I've written down. At 298 and 1 bar. So of course delta G0 is equal to minus RT ln. Now we have all these activities. So the activity of this AO2, Si2O5, etc. in kaolinite times the activity of K plus squared times the activity of SiO2 in quartz to the fourth divided by the activity of KAl Si3O8 in feldspar squared times the activity of H plus squared times the activity of water. So we put RT on the other side, and what we do is we convert to logs to base 10 for reasons which I think will become clear in a moment. So we convert to log to base 10, and 2.303 is the conversion factor. So 2.303 log to base 10 of x is equal to ln of x. Okay, so we divide delta G0 over 2.303 RT, and we bring the negative sign on the other side, and that's going to equal log, and let's suppose that all our activities that we have pure kaolinite, we have pure K feldspar, we have pure quartz, and that the water is essentially pure. So we set all those activities to 1. Now in their standard states. So that then will equal log K plus squared over H plus squared. Let's just do the calculation. So this is minus 40,900. So this is 40,910 over 2.303 times R, which is 8.314 times 298 equals log K plus squared over H plus squared. And that is what I did earlier, 7.17. And if we take the 2 outside, so we use the properties of logs to separate the potassium from the hydrogen. So that will be 2 log K plus minus 2 log H plus. Now everybody knows, I think, that the negative log of the H plus concentration is also known as pH. So minus log H plus is pH. So that comes to be 7.17 equals 2 log K plus 2 pH. Let's divide by 2, so that's going to be 3.58 is equal to log K plus pH. So what does that mean? Well, let's suppose that we have rain. Rain is falling on our granite building, rather a shame. It's glistening there in the rain, and the hydrogen ion, which is in the rain, obviously acid rain, it might be more of a problem somewhere in the old East Germany where the rain was pretty acid from beautiful clean cities in Britain. But what's going to happen is that the hydrogen ion is going to get consumed by reacting with the feldspar, making small amounts of that and releasing potassium. And that will continue if we took a chunk of our granite, imagine it, for example, at the bottom of a pond. Ponds are usually fairly dilute, but at the bottom of a pond, the same would be going on. And that reaction would continue until when? Well, it would continue until we reached equilibrium. Okay? So if we can imagine our feldspar reacting away at the bottom of a static pond, it will react until the local concentration of potassium and the local concentration of hydrogen reach equilibrium. When will that be? Well, it's when this condition is met. This is the condition of equilibrium. 3.58 is log K plus pH. So suppose we have pH 7, nice and neutral. Which as you recall, that's neutral pH. Bring minus 7 on the other side. It will be minus 3.42 is equal to log the K plus. So at equilibrium, if our pond is nice and neutral, it will continue reacting until the potassium concentration, log of the potassium concentration reaches minus 3.42. We anti-log that, that means that the potassium concentration is equal to 10 to the minus 3.42, which ain't very much. Get my minus 3.42, 3.8 times 10 to the minus 4. Molar. Okay, not very concentrated, but on the other hand, if our nice little pond was full of mine tailings, which could be pretty acid, let's suppose pH is 3. Or let's say 2. At pH 2, we put 2 there, put it on the other side. The potassium ion concentration at equilibrium is going to equal 10, I'll get this right, 2 over there, 1.58, 10 to the 1.58 molar. Okay, so our concentration has gone up, of course, by 5 orders of magnitude, the equilibrium concentration, by lowering the pH from 7 to 2. So 10 to the minus 1, 10 to the 1.58 is 38 molar. Which is 38 moles of potassium per kilogram of water, which is, potassium is 40, mass 40, so there'll be more, on a mass basis, there'll be more potassium than water. Well, of course, our infinite dilution standard state isn't going to be able to treat concentrations this high. We'll treat these sorts of concentrations very well, but at this concentration, there'll be all kinds of weird things going on in solution, and it's no longer, the potassium ions will be interacting quite strongly with one another because there's so many of them. Okay, so that's what's going to happen. Is the hydrogen ion in solution will react with the feldspar, drive it this way, release potassium. That will continue until the potassium concentration reaches the equilibrium amount. Okay. What I'm going to do now is I want to give you a way of expressing these relationships on a diagram. And to illustrate that, I'm going to take a reaction which is similar to the one I just talked about, the breakdown of feldspar by reaction with acid to form kaolinite. But I'm going to start with the assumption that the solution is not saturated in silica. Okay, in this example that I gave you, I'll bring it down again, I've assumed that all the silica is just produces quartz during the breakdown reaction. Now, in general, that implies that we have equilibrium between all the solids, which may or may not occur. But let's consider the case where our starting solution is completely devoid of silica, so that the silica that's released is actually released into solution. So here, if I could just remind you, I've assumed all the silica produces quartz. Rather simplistic assumption, but it gave me the in to bring in pH and talk about potassium ion concentrations at equilibrium. Let's consider perhaps something a bit more realistic, in which the potassium feldspar releases silica in solution. And we know that that then will be H4SiO4. Oh, there was one thing I meant to mention, and that is that we have done something we've done here in order to balance this reaction. I'm sure nobody questioned this, but in order to balance this reaction, I assumed that all of the aluminium was in a solid. That is, that the solid in the aluminium in the feldspar was transformed completely into aluminium in the kaolinite. I also did the same with the silica. But in general, when we're writing down these weathering reactions, we balance the aluminium in the solids. And the reason for that is that aluminium is the least soluble element. Okay, silica is more soluble than SiO2 is more soluble than aluminium. So we balance the reactions by assuming that no aluminium is released into solution. That's the normal way of doing it. So let's take the slightly more complex case where in solution we have potassium, hydrogen, and silica. And the reaction is very similar to the one we just did. Plus 2K plus H4SiO4, 0. That's our solution. Make sure I balance that. Okay, so we've got to balance the silica, so we got 6, 2 there, so we need 4 of those. And now to balance the hydrogens, we're going to need quite a lot of water. So we've got 16, 20 here, 2 here, so we need 9 waters. That being now in solution. And we should just check the oxygens. That is 16 and 9 is 25. 5 and 4 is 9. And 16 is 25. Wow, good. Okay, and for that reaction, delta G0 is plus 41450. Is that right? Plus 41450 joules. And delta G0 minus delta G0 over 2.303 times 8.314 R times 298 is the log of the equilibrium constant. Okay, we wrote out the equilibrium constant fully last time. So something I want you to note is that in the same way that we can add and subtract delta G or delta H or delta S for one reaction to make another reaction, we can do the same with log K, because log K is just a linear combination of delta G's. Okay, so log K can be added and subtracted at constant pressure and temperature in the same way as we added and subtracted enthalpy, entropy, and volume. Okay, so that's the log then. We'll write this out of the activity of this kaolinite beastie times K plus squared times H4SiO4 to the fourth power divided by activity of the K feldspar H plus squared and the activity of water to the ninth. We use the same standard states as before, so pure solids and pure water, so those activities are all 1. This over here is minus 7.264. And that's going to equal the log of K plus squared times H4SiO4 to the fourth over H plus squared. Okay, so let's separate this, and I'm going to do it in a slightly different way. So minus 7.264. I'll take the silicon outside. So that's log K plus squared over H plus squared plus log H4SiO4 to the fourth just come up here, rub that out. Okay, we can take the 2 goes outside here and the 4 goes outside there, so minus 7.264 equals 2 log K plus over H plus plus 4 log mustn't go up too high here. 4 log H4 SiO4. This thing isn't really good. So let's divide through by 2. So minus 3.632 equals log K plus over H plus 2 log H4 SiO4 one equation, 2 unknowns, not terribly easy to solve. But what we can do is, which is quite informative, is we can plot a diagram for this equilibrium. Remember, this is our equilibrium condition. So at equilibrium, when we have equilibrium between the feldspar, the acid in solution, kaolinite, the potassium, and the silica in solution, this condition is met. This will be our condition of equilibrium. So we can plot a diagram of log K plus over H plus against log H4 SiO4. So, what numbers shall we choose? Well, the important point to remember is that this H4SiO4 in solution never goes much above 10 to the minus 3, i.e. molality of 10 to the minus 3. So we're looking at numbers that are all down below that. So why don't we put in minus 8? So if we put in minus 8 here, we've got minus 16, put it on the other side, plus 16, it's 12.368. So that would be our K plus over H plus. We'd have a lot more potassium than we would have hydrogen in solution. And then if we put minus 4, let's say minus 4, obviously the slope is minus 2, but anyway, 2 times 4 is 8. Add to minus 3.632 is 8.368. Sorry, 4.368. So that would be 4. And this, of course, is an equation of a straight line. So we draw a straight line. That's the equilibrium line. And the equilibrium line on this diagram is called an activity diagram. And it's the same as any other phase diagram, but it just deals in activities of the components. All right, and this is at fixed pressure and temperature, so this is at 1 bar, 298 degrees K. Those are conditions that I got for those are G0 and this thing here. And now we have the difficult question, which is, that's the equilibrium line. Which phase is on which side of that line? So is kaolinite here at low K plus over H plus, or is kaolinite here at high K plus over H plus? Okay, now in order to figure that out, if it's not intuitively obvious, we use Le Chatelier's principle. Now, Le Chatelier's principle says that At equilibrium, if you apply a constraint to a system, the system will respond by trying to remove that constraint. All right? So if we increase the potassium ion concentration, the system will respond by reacting that with kaolinite and making feldspar and releasing hydrogen. Okay? So as the higher in potassium, the more potassium we pump in, the more feldspar we make. So feldspar is on the high potassium side of this line. And kaolinite is on the low. Opposite argument, if we pump up hydrogen ion, pumping up hydrogen ion is lowering this. The system will respond by reacting the feldspar to make kaolinite. Okay? So pumping up the hydrogen at low K plus over H plus, the system responds by making kaolinite, releasing potassium and silica to solution. Okay, there was one other thing I was going to say, I can't remember what it was. So this is Le Chatelier's principle. That the system responds by trying to remove constraints. Okay, in the practical, I'm going to ask you to take this reaction and to look at some other reactions that are related to feldspar and kaolinite and muscovite, which is the other phase which is common in this system. Okay, as I said, activity diagram is just like a PT diagram. You can use the same principles. You can calculate invariant points and univariant lines. This is a univariant line on an activity diagram. Okay, that will do. Thank you.